Today we'll start a new topic, that is phase diagram and phase transformation. So first we will take up with the phase diagrams part.
The recording on.
Hi, recording.
Sandeep is taking care of that.
You are supposed to take care of that.
হ্যাঁ স্যার হচ্ছে স্যার আপনি ইয়ে করতে পারবেন না আমরা করছি স্যার
Hmm. Okay. So you have idea about the different phases of any matter. So normally we have three different phases: solid, liquid, gas. Now, when we are discussing about the phase diagrams of solids, particularly for different metals and alloys, it is slightly different than your liquid or gaseous phases. We will be here mostly concerned with the solid phase diagrams. So some of the basic definitions that are required to understand the different aspects of solid phase diagrams are: so these are some of the terms that are used for discussing the phase diagrams, like system. System, this term is used in somewhere else also. You have studied the thermodynamics.
থার্মোডাইনামিক্স হ্যাঁ স্যার
In thermodynamics, you have got this system definition, but here we will slightly, relate this particular term to a phase diagram. Now, when we are talking about the system, it is basically a body of engineering material under the investigation, which are composed of solid, liquid, and gases, and or maybe the combination. Like suppose you are mixing silver and copper, so it is becoming silver copper system, like that. Then there can be the combination of other materials like NiO, MgO, like that, or even sugar milk system, like that. So we'll term the combination of two or more elements or metals as the system here. The component of a system is obvious. The ingredients which will be there, like it can be two metal system. So those are called the components, like copper, silver, or Fe3C. So there can be two or more components. So each of those components will be consisting the system. Then comes the phase. You know what is a phase? So phase is basically a homogeneous portion of a system that has uniform physical and chemical characteristics. It can be pure material, solid solution, liquid solution, gaseous solutions, like that. There can be a single phase system when you are considering about the single substance, or there can be a multi-phase system. So here mostly we'll be discussing about the multi-phase systems, definitely consisting of two or more components. So multi-phase systems and single phase systems. Now, components and phases. You see, you might have seen the microstructure in diagrams. In fact, you will study the microstructure of different common and extensively used materials in our metallography lab in your third year classes. So there will be a lab to study the material composition, and also will be trying to relate those micro constituents or composition with the property, and particularly your emphasis will be to relate those uh, microstructure with the mechanical properties. If the microstructure changes, then the mechanical property also changes. So microstructure and micro constituents plays a very important role in determining the mechanical properties. That is the objective of the metallography lab. So that we'll be studying. So here is one, just to give you an idea about what is microstructure, how it looks like. This is a diagram of aluminum copper alloy. and this is this for a particular composition, maybe certain percentage of aluminum and remaining copper. So when this alloy is existing in solid phase, when it is in solid phase, obviously you will see the two different phases, we call alpha phase and beta phase. So see this composition and the microstructure will be different for different percentage of composition. So that we will discuss in detail how it changes. So this is one diagram where we can see the two important phases in the microstructure. So the whole diagram is called the microstructure of copper aluminum alloy. So what are the microstructures you can see? We can see the microstructure of beta phase and we can see the microstructure of alpha phase. We are typically terming these two different phases, solid phases, alpha and beta phase. Normally, when we will be talking about alpha, beta, or gamma, something like that. Normally, those terms are used to denote the solid phase only. Those terms are used to denote the solid phase. So here, in case of copper and aluminum alloy, we have two elements. So those are the two components, and this diagrams gives you the phase. It is the phase, different phases mixed in this microstructure. So next comes the phase diagram. Phase diagram. So it is a graphical description of kinds and amounts of phases that can be expected in an alloy as a function of composition, temperature, and pressure. So obviously, the phase diagram will change with respect to composition, temperature, or pressure. Here at this point, I should mention that when you are talking about the solid phase diagram, the role of pressure is not that significant. But in case of liquid or gaseous, phases, the pressure may be a very important factor or parameter. So this is the phase diagram. There can be unary, binary, or ternary, even quaternary phase diagrams. Unary means only single component is there. Binary 2 components, ternary 3 components, then quaternary 4 components, like that. So as you increase the number of components, the more complicated will be the phase diagrams. So this is the phase diagram. Then comes the microstructure. Microstructure is a very, very important term when you are discussing about the mechanical properties of alloys or any material. Microstructure plays a very important role to determine the mechanical properties, and you will be interested to know the mechanical properties while designing some component or selecting the materials. So a system's microstructure is characterized by the number of phases present. Each and every phase will determine the microstructure and also their percentage contribution, and other factors are also there. Actually, not only the components but also there is a term called heat treatment. Will be studying the heat treatment in detail, because heat treatment also plays a very important role in determining the microstructure. So see, so many factors are there which influence the microstructure, and microstructure on the other hand influences the mechanical properties. So microstructure is a systems. It is basically characterized by the number of phases present, their proportions, and the manner in which they are distributed or arranged. Now this term, the manner in which they are distributed or arranged, this distribution and arrangements are actually influenced by the heat treatment process. So factors affecting microstructures are alloying elements present and their concentrations, and this is the term, and the heat treatment of the alloy. Heat treatment is a very, very important, technique by which you can modify the microstructure and thereby change the mechanical properties. If you want to increase the ductility of the material, you can do that. You can increase the hardness of the material. You can make the material more softer, so many different methods are there by which you can change their mechanical properties according to a requirement by following the heat treatment processes. So microstructure is very, very important term. There is a difference between macrostructure and microstructure. Details you might be, taught in your metallography lab. Also, we'll be discussing here microstructure. Macrostructure is basically nothing but the, when you are looking at the structure without taking help of some instruments, magnifying instruments. So when you are looking at some material and the overall picture you are getting of the material, that is called the macrostructure. So microstructure is very important here. Next comes the phase equilibrium. The state of a system where phase characteristics remain constant for infinite period of time and the free energy is minimum. We'll be discussing about, something about free energy, probably free energy. We'll be talking about this also in subsequent slides. So when the different phases are at equilibrium, we call that this is the phase equilibrium. The system is in equilibrium. So then there is a term called the solubility limit. We'll show it. Solubility limit is basically the maximum concentration of solute atoms that may dissolve in a solvent to form the solid solution at some temperature. We'll see this with some example. Now, what are the importance of phase diagrams? It's very important to understand the alloying details, their properties, compositions, so many, because you might be interested to know the composition and their properties at a particular temperature also, how it varies. So many factors are there. So all these, you will get some visual pictures from the phase diagrams. You will get some idea. So there is a strong correlation between microstructure and mechanical properties, and the development of alloy microstructure is related to the characteristics of phase diagrams, which I have already told you. Now the phase diagrams provide valuable information about the melting, casting, crystallization. Say when you are manufacturing, when you are going to manufacture some components with the help of casting. So obviously you must have to have the idea about the melting point and crystallization parameters of that particular material. So the phase diagrams will give you the visual picture and will give you the idea about the melting point and what is the crystallization patterns of the materials, when it will start crystallizing and all that. Everything we will get from the diagram. So it gives the visual picture of different phases under various composition, temperature and pressure. Now, just to understand the idea, it is just to give you some idea about the different phases and the equilibrium condition and also the solubility limit. We have taken an example. It is not from the examples of metals, but it is just a common example. We know sugar water solution, and we are trying to understand the solubility limit of sugar in water. So if we try to draw a diagram like this, see, in the x-axis you are taking the composition and y-axis you are taking temperature. So with respect to temperature, you see the solubility limit of sugar varies. So in the x-axis you are increasing the composition or weight percentage of sugar, and in y-axis we are taking the temperature. And if we try to draw a diagram taking the solubility limit. Solubility limit means basically the maximum concentration for which only single phase solution exists. So we'll find that this is the green line which indicates the solubility limit. So when we are increasing the temperature, and also we are increasing the composition, so solubility limit changes like this. Let me give you another. So from here we can understand that. So for a particular composition, say we are taking a composition of 65% sugar, we find that if the temperature at a particular temperature, say 20 degrees centigrade, we are getting this. So at 20 degrees centigrade, if concentration is less than 65%, it is called the liquid solution. It will be in liquid form. It will be in, which is called, actually this is the mixture of sugar and water, which is called the syrup. But at the same temperature, if you increase the concentration, it will be solid plus liquid composition. So there will be no, there will be partly liquid and partly solid. So there will be mixture of liquid and solid. So here actually you are getting two different phases. On the right hand side we are getting two different phases. On the other hand, at this particular temperature, we are getting only one liquid phase when constant composition or composition percentage is less than 65%. So basically there is a line here which actually demarcates between the liquid phase and liquid plus solid phase. Technically, we will call this line as liquidus line. We will see it in phase diagram. This line will be a liquidus line, which actually demarcates the liquid phase with the liquid and solid phase. So this is the idea. This is the idea. This diagram will give you the idea of how solubility changes with temperature and composition. So obviously, if you look at this diagram, there is an effect of temperature composition on the phases. So here we have that A, B, and D. So AB line, vertical line. So what we are doing, we are keeping the composition constant. Let us say at 70%, composition remains constant, but we are changing the temperature only. So obviously, with the rise of temperature, what will happen at this particular point, that on the line, on the blue line, this is the solid liquid phase, but beyond that it will be only the liquid phase. So even without changing the composition, it will change the temperature, the phases will get changed. On the other hand, there is another possibility that you are only changing the temperature, you are only changing the composition without changing the temperature. The horizontal line from B to D, even then your phase will get changed. Number of phases will get changed. So these are some of the possibilities are there. So this will be required for our phase diagram, for analysis of phase diagram. So this diagram you are well known with. This is called the phase diagram of water. So this is a single or one component phase diagram, and we have taken here two important parameters, that is pressure and temperature. So the phase diagram of water looks like this. On the left hand side you have got the solid ice, then you have got the liquid phase, then vapor phase. So at point O, all the three phases are at equilibrium, which is called the triple point of water, that you know. So this is basically the phase diagram looks like this. The phase diagram looks like this, but it is, let us now go to the solid phase diagrams for metals and alloys. But before that, we require to know an important rule which is known as Gibbs phase rule. Gibbs phase rule. Now this rule will give you some important information. What are the information that you will get, that we will see? But let us understand the phase rule first. So phase diagrams and phase equilibrium are subject to laws of thermodynamics. Gibbs phase rule is a criteria that determines how many phases can coexist within a given system at equilibrium. So here small equation has been written: P plus F equal to C plus N. P indicates the number of phases present, F indicates the degrees of freedom, and C indicates the number of components, and N indicates the non-compositional variables, number of external factors like temperature, pressure. Now to understand this rule, let us discuss some example. What is the implications of this equation? That is important. Now let us take an example of copper silver system. Let us take an example of copper silver system. And if we see the phase diagram at a particular, let us say, pressure, here pressure is a not that important factor, and we are considering a single phase. So since pressure is not important, so number of external factors n, this n, normally temperature and pressure, but for metallic system, effect of pressure is not that significant. So we can consider n equals to 1, only temperature.
So
And
basically, it is independent of pressure then.
solid system doesn't affect. You see, if you apply the pressure, it will not affect the phase diagrams to that, not that significantly. So that is why I do not consider pressure as a very important factor. So, but for liquid and gaseous phase diagrams, it may be. It is definitely it is a factor.
Okay, sir.
That is why n we have taken as 1. Instead of 2, we are taking only temperature, so n equal to 1. So we have got two components here. We have two components, copper and silver. So C equals to 2. And P, we are taking a single phase. We are considering in a single phase region. Now, suppose we know N, C, and P, then you will be able to find out what is the degrees of freedom. Now, degrees of freedom, the idea of degrees of freedom is basically number of independent variables which can be changed without changing the number of phases in equilibrium. So what is happening, what is the significance is that when you have got number of degrees of freedom equals to 2, that means in order to characterize this alloy in a single phase region, you need to have two parameters to be given. So if you keep temperature and composition both, if you know temperature and composition, then only you will know what is the equilibrium position in that single phase region. So the degrees of freedom will actually give you to or indicate the number of factors that will be required to explain, to completely characterize the system in that particular phase. Say another example, we are taking another same example, but we are changing the phases. You see, if we take P equals to 2, if we take P equals to 2, that means we are considering in a region where alpha, that means where solid and liquid both are there, mixture, alpha plus L or beta plus L, or maybe alpha plus beta, two-phase region. That means P becomes 2. And if you put this into this equation, I will get F as 1. It indicates that number of degrees of freedom is only 1. So if we keep either temperature or composition, or if we have temperature or composition, then we can completely define the system. That means only one parameter will be sufficient to completely define the system under equilibrium condition. And another we are taking, we are taking the three-phase or three-phase exists for a binary system. Then there will be, if you can calculate here with the help of that equation, you will get F equals to 0 degrees of freedom. This means that the composition, the composition and the temperatures are fixed. This condition is met for eutectic system by the eutectic. Actually, this we'll discuss it when we will discuss about the eutectic system. What do you mean by eutectic system? Where solid and two different phases are at equilibrium at a particular temperature and a particular composition. So this means that the composition and temperature will be fixed for this particular when three phases coexist or three phases are at equilibrium. We will see this in detail in subsequent slides, then it will be further clear. Now let us take one example. Let us take one example to understand the further explain the Gibbs phase rule. Now determine the degrees of freedom and composition in a copper 40% nickel alloy at 1300 degrees centigrade, 1250 degrees centigrade, 1200 degrees centigrade, and explain the significance. So we are trying to explain the significance of this phase rule with the help of the diagram. So this is a metallic system, metal system. So Gibbs phase rule can be modified as P plus F equals to C plus 1. We have taken N equal to 1 because pressure is neglected and only temperature is considered. Now let us see how these phase diagrams look like. So copper nickel system. If you draw the copper nickel system phase diagram, it will look like this. In the x-axis, we are taking nickel, nickel and copper percentage. So we are denoting only nickel here. That means when 100% nickel is there, copper percentage is 0. So here on the left hand side, when nickel percentage is equal to 0, that means copper percentage is 100%. Copper is 100%, and in between there is the mixture. And in the y-axis, we are taking the temperature. So you see, when nickel is 0, then 100% copper, that means pure copper. So pure copper has got a melting point somewhere here. This point indicates the melting point of pure copper. On the other hand, this particular point you see on this right hand side, this point will indicate the melting point of nickel, pure nickel. Now, if you mix nickel and copper, you will get different mixtures with different compositions, and their melting point and their compositions will vary something like this. You will, if you, and how can you draw? You see, how can you draw this type of phase diagram? See, obviously this is a phase diagram. So this particular phase diagram, we call it a phase diagram with complete solidity. That means these two components will be completely soluble in solid, uh, completely form a solid solution, But you will come across some examples where when the components are in solid phase, they will be separated out with no solid solubility. They will be when they will be in solid phase, they will get separated out. So though there are also phase diagrams like that, but this is one type of phase diagram. We will see what are the different types of phase diagrams. So this is a phase diagram where the components are completely soluble in solid phase also. Now, if you, how can we draw this? So actually, in order to draw this, we'll have to take different compositions, and you'll have to perform the phase transformation by raising the temperature. You'll have to note down when the solid is starting melting, and then when the complete melting is, when the melting is completed. So by that you will get two different you will get different points. So this solidus line is basically is those points when the liquid phase and solid phase actually transforms into completely solid phase. So you will get different points, and then if you join these points, you will get a solidus line. Similarly, when the liquid phase, when you are, suppose you are at a higher temperature, you are reducing the temperature, and the liquid temperature is getting reduced, and ultimately at a particular point you will find that the liquid starts solidifying. So first, the starting point of the liquid, when it starts solidifying, all these points will be on the liquidus line. So there will be two different lines, solidus line and liquidus lines, and in between there will be a region, or there will be a phase which will be mixture of liquid and solid. So we are calling it L plus alpha. So, so in this case, you have got three different regions. One is liquid region, then solid region, and also the mixture region. So, so far as this problem is concerned, let us consider when you are at 1300 degrees centigrade, and for this particular alloy, we are taking nickel percentage at 40%. So at 40% nickel and 1300 degrees centigrade, we are at this particular point, point A. So this is in the liquid region. Now what we are doing, we are, so let us first see that this one. So at A, so when we are at A, that means phase is only one, liquid phase, so P equals to 1. And number of components, we have the copper and nickel, so two components. So obviously we are getting F equal to 2, which indicates that we must fix both temperature and composition to completely describe the state of copper nickel in the liquid region. So you require to know two variables, temperature and composition, to completely describe the state of copper nickel alloy in the liquid region. So that is what the degrees of freedom indicates. Now, if we are at point B, just we are reducing the temperature to some extent, and we are in the two-phase region at point B. So it is in the two-phase region. So here our number of phases becoming is 2. P is 2 now. T equals to 2, which indicates that F equals to 1, which indicates that degrees of freedom equals to 1, which indicates that only one variable is to be fixed in order to completely define the system. So indicates that if we fix the temperature of the two phases, the composition of the two phases are also fixed. So if you fix one particular variable, then another variable is automatically fixed. Or if the composition of that particular phase is fixed, then temperature and composition of the second phase are automatically fixed. So basically, the meaning is that when degrees of freedom is 1, so only one parameter or the variable is required to be fixed in order to completely define the system. So similarly, when you are coming to the solid phase at 1200 degrees centigrade, when you are at 1200 degrees centigrade, then you are at point C, which is in the solid region, completely solid region. So here you have got only one phase. So similar to that, you will have to define both temperature and composition to completely describe the state of the solid. So this is the significance of the Gibbs phase rule. And here are some points also. So from that you can understand. Here one point I should tell you here. This horizontal red line in the two-phase region, this is called the tie line. And this tie line will help us. This tie line will help us to determine the at this particular temperature, let us say 1250 degrees centigrade, what will be the percentage of liquid and solid phase, that we can calculate. There is a rule called Lever's rule. The rule is called Lever's rule. We will discuss that. With the help of that Lever's rule, you can calculate at a particular temperature what will be the percentage of liquid and solid phase in the mixture region or the two-phase region. So you see at if you vary the temperature, your percentage of solid and liquid phase also varies as you vary the temperature. So at each temperature, this percentage will be different, and obviously, the alloy percentage also will be different. Next, The solid solution. Solid solution. I think we have discussed in our when we are discussing about the equation and all that. So we have discussed this part, solid solution, two types of solid solution, substitutional and interstitial solid solution, that we have already discussed. So I'm just keeping this slide. Now there's an important rule. There is an important rule called Hume-Rotheris rule. Hume-Rotheris rule. It is an empirical rule that governs the choice of alloying elements in the formation of substitutional solid solution. That means which are the components which will form the solid solutions, that is governed by this particular rule. Hello. Just 1 minute. I have a call from HOD. हेलो हाँ 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 हाँ
Sir, would you please turn off the presentation because you might be doing some university work that way?
अच्छा अच्छा 1 मिनट धरो तो 1 मिनट धरो तो अच्छा अच्छा today I have an important talk to HOD, so today I am just okay ending here.
Okay, sir, no problem, sir. Thank you, sir. Then we are disconnecting ourselves.
Okay, sir. Thank you.